So now, let's see a little demo of this system. So here, well, this is Eclipse, and it's the Cedalion workbench, showing you an example identical to the one we just described in Prolog. So if I click my mouse here, you can see that instead of getting a cursor like we would for conventional text editors, we can see here this dotted. You can see this dotted frame around whatever construct I click. This is something you would expect from such projectional editors. Now, whenever I click here, you can see that here in this bar, I see a Prolog-like textual representation of the same construct. This allows me to edit stuff. Now, the first part, as I said earlier, is the DSL definition. So here we define our four constructs: the empty string, a terminal, concatenation, and a production rule. We have each such definition has two parts. It has type signature and a projection definition defining how it is visualized. So the for example, the empty string is visualized using Unicode symbol 949, which is this epsilon. So what happens if I change it to 948, for example? And I save it to make it light, and you see that it changed into a delta. When I undo it, it's back where it was. Below the DSL definition comes the DSL implementation. Well, the first thing we need to do here is to define the parse predicate. Remember from the previous example, but here we have to give it a type signature, and we also choose to give it a projection definition. So the parse predicate, which you can see here as in its Prolog-like textual form, is actually visualized using the double arrow and the slash. So here we have four clauses or four statements that define the semantics of our four language constructs. Below them, you can see our two production rules that depict that make our application, quote unquote. And now they are preceded by a type signature for the S symbol, because it is a new concept that is defined here. So what happens if I will delete it and save? Then, well, Prolog's type system would say, I don't know what S is. But that's not a very big problem, because as you can see from this tooltip, it already knows what it's supposed to do. So when I double click it, it suggests how to fix it, and when I apply the change, everything is back to normal. Now, below these, we have two unit tests. One for testing that AABB is acceptable by our grammar, and AAABB is not. This is the negation operator. And so, if, for example, I will break this grammar and save, I will get an error instantaneously. My unit test will just fail. Remember, it uses a validator for that. So when I undo the change and save, we're back in business. So let's go back to the slides. Some related work. The most notable related work are the method programming system and intentional workbench, which intentional domain workbench workbench, which are language workbenches intended to support the LOP process, dedicated to implement and use DSLs with projectional editing. The difference between them and Cedalion is the fact that they use external DSLs versus Cedalion's internal DSLs. There is also an interesting work by my colleagues at the Open University on Model Talk, or their descendant Inc. So to conclude, Cedalion is a proof of concept. It proves that the combination of getting the ease of defining internal DSLs and the power of in defining syntax and semantics usually associated with external DSLs, well, this combination is possible, but there's still a long way ahead of us and a lot of things to do. Thank you very much.